You've probably been there, right? You build a model and it looks incredible on paper. We're talking near perfect scores. You think you've cracked it, and then you unleash it on the real world and it just bombs, completely fails. It's one of the most frustrating mysteries in data science. So today, we're going to put on our detective hats and investigate the #1 culprit behind this kind of deception. We're talking about overfitting.
All right, here's our game plan. First, we're going to define the crime scene, what we call the perfect fit problem. Then, we'll line up the 5 usual suspects, the root causes of overfitting. After that, we'll break out the forensic tools to spot the deception, open up a toolkit to fix it, and finally, lay down the law on how to build a model that's actually credible.
Okay, let's dive right in. Section 1, the perfect fit problem. This is all about that strange situation where a perfect score is actually a failing grade. So what is actually going on here? Why do these perfect models fail so badly? Well, think of it like this. An overfit model is like a student who gets a copy of the practice test and just memorizes the answers. They don't learn the concepts, they just memorize question 1 is B, question 2 is D. Sure, they'll ace that practice test, but then you hand them the real exam with different questions and they're totally lost. That's exactly what's happening inside our model. So let's get a bit more technical. The official term is overfitting. And what it means is that our model gets a little too smart for its own good. It doesn't just learn the real underlying patterns in the data, that's what we call the signal. It also starts memorizing all the random, accidental little quirks and flukes in the specific data we trained it on. That's the noise. It's like it's memorizing the static on the radio instead of the actual song.
And this right here, this is the smoking gun. You get this massive, totally misleading gap in performance. On the training data, the stuff it's already seen, performance is through the roof. But the second you introduce it to new, real-world data, the performance just tanks. This huge drop-off, that is the classic signature, the telltale sign of an overfit model.
Okay, so we know what the crime looks like. Now it's time to find out who did it. Let's move on to the 5 root causes. How exactly does this sneaky overfitting get into our models in the first place? All right, culprit number 1, excessive flexibility. Imagine a model that has way too many parameters. Think of them as thousands of tiny little knobs and dials. With that much complexity, the model can literally twist and bend itself into a crazy shape just to perfectly hit every single data point you give it. But that includes all the noise. What you end up with is this super jagged, unstable line that's completely useless for predicting anything new. Next up, cause number 2, a limited sample size. You know when you just don't have enough data to work with. If the information is thin, or the signal you're trying to find is really faint, even a simple model can start finding patterns that are just, well, random chance. It's kind of like seeing shapes in the clouds. Yeah, you can see a dragon if you stare long enough, but it doesn't mean anything. This gets really dangerous when you combine it with our first culprit, an overly flexible model.
And that brings us to cause number 3, high dimensionality and what I call aggressive searching. Look, if you throw thousands of potential features or variables at your model and just let it search for the best ones, you're pretty much guaranteed to find something that looks amazing just by pure luck. It's like if you torture the data long enough, it'll confess to anything. The more you search, the higher the risk you're just finding a fake pattern, a spurious correlation, and building your whole model on a foundation of sand.
Oh, this next one. Cause number 4, data leakage. This is a huge one, a real cardinal sin of modeling. It's when information from the future or from your precious test set accidentally contaminates your training process. You think you're keeping them separate, but you're not. And it can be super subtle. Something as simple as calculating the average for standardization across your entire dataset before you split it, boom. You've just leaked information from the test set into the training set. It completely invalidates everything.
And our 5th and final culprit is what's called a distribution mismatch. Simply put, the world changes. A model you trained on customer behavior from 2019 might be totally useless after 2020, right? The underlying patterns, the relationships in the data, they've shifted. This is sometimes called concept drift, and it's a tricky one because your model might have been perfectly fine when you built it, but by the time you deploy it, the world has moved on, making it look overfit.
Okay, we've rounded up the suspects. Now how do we catch them in the act? Time to open up the detective's kit. Section 3 is all about the forensic tools we need to spot the deception and diagnose overfitting.
So when it comes to fighting the evidence, not all tools are created equal. Think of this as a hierarchy of validation. At the bottom, you have a simple train test split. It's fast, sure, but it can be really unreliable. You might have just gotten lucky with your split. As you move up the ladder to things like k-fold cross-validation, and then to the top with nested cross-validation, your methods get way more rigorous and trustworthy. And here's the key rule. The more you searched and tortured your data to find a good model, the higher up this ladder you need to go to validate it. Nested CV is really the gold standard for an honest evaluation.
And a proper diagnosis isn't just one simple check. It's more like a full-on forensic investigation. You've got to run a whole battery of tests. First, you compare that in-sample or apparent performance with your cross-validated performance. Is there a big gap? Then you dig deeper. You don't just look at something like AUC. You check if the model's probabilities are actually well-calibrated. You quantify how unstable the model is across different samples. And finally, you have to do a sanity check. Do the results even make sense? Are they plausible?
All right, so we've spotted the deception. We've got the evidence. Now what? Time to bring in the big guns. Let's open up our toolkit for correction and see how we can actually prevent and fix this mess.
Two of the most common and powerful tools in our kit are called Ridge and Lasso. They're both types of penalization. Basically, they work by putting a kind of leash on the model, preventing it from getting too complex and crazy. Ridge is kind of gentle. It shrinks the coefficients of correlated predictors, making the model more stable. Lasso is the tough one. It's more aggressive and can shrink some coefficients all the way down to 0, which means it's also doing feature selection for you. Pretty cool.
We mentioned nested cross-validation before, but let's really break it down because it's so important for honest tuning. Think of it like this. You have two loops. The inner loop is like your practice field. That's where you try out different models, you tune your hyperparameters, you experiment freely on a subset of the data. But the outer loop, that's the judge. It holds back a piece of data that the inner loop never, ever gets to see. Once your inner loop has picked a winner, that chosen model gets tested exactly once on that outer holdout data. That single score is your final, honest grade. No do-overs, no peeking.
And this leads us to maybe the single most important rule in this entire process. If you remember one thing, let it be this. Split your data first. Seriously, before you do anything else, before imputation, before standardization, before any pre-processing, you have to lock your test set away in a vault. All the learning, like figuring out the mean to scale by, has to happen only on the training data. Then you just apply those learnings to your test set. Never, ever fit on the whole dataset.
Okay, we're heading into the home stretch. We've talked about tools and techniques, but really, building a credible model goes deeper than that. It's about having a disciplined process from the get-go. It's about the principles you follow.
So here it is, the code of conduct for building a model you can actually trust. First, you lock in your evaluation plan before you even start modeling. No changing the goalposts halfway through. You should always prefer simpler models, or use these regularized learners we talked about. You have to tune honestly with methods like nested resampling. And you don't just report the best score, you report the optimism-corrected performance. You stress test it. All of this is about building a process that protects you from fooling yourself.
And really, this quote says it all. The goal isn't to present a model as credible because it has some flashy high score. The goal is to present a model as credible because the process you used to build it made self-deception almost impossible. It's about the rigor, the skepticism, and the discipline that went into it. That's where true credibility comes from. So I'll leave you with this final thought. The next time you see a model, maybe one of your own, with an almost perfect score, I want you to stop and ask yourself, is this model persuasive, or was it just lucky? Is its success built on a rock-solid skeptical process, or did it just happen to find a random pattern in this one dataset? Because really, that answer changes everything.